So good afternoon, everybody, and thank you very much for having me. And we've heard about other stars, and there were some mentions of the Sun. So indeed, I'm a senior lecturer in the math department in the Center for Geophysical and Astrophysical Fluid Dynamics, and my field is on space weather, the connection between the Sun and the Earth. So I wanted to give you some modern views of what we call heliospheric research, and so it's about space weather and plasma. And this is a nice picture first of the aurora that you may have seen in pictures or have seen yourself. And so I would like to say that, Exeter is a special place in the history of space weather. We believe that Exeter was the place where the first recorded impact of space weather on civilization occurred. So we are talking here about mid-19th century, 1841, and there was at the time the railway company, Western Railway, passing by, and you had a train between Starcross and Exeter that was delayed by 16 minutes. Why? Because at the time the trains were, there was communication, and the go-ahead was given by telegraphs, and the telegraphs had been affected by an intense solar storm, solar disturbance. At the time, these connections were not easily made. So we are looking back retrospectively at an event that we believe was affected by a geometric disturbance. But it's nice for you guys to know that this was the first impact on civilization was here. So 18 years later, 1859, so we have what we call the Carrington event. So what we have here in these slides is my experience of the Carrington experience. So 1859, Carrington was looking into his telescopes, no filter, just white light images, and he saw this very intense flare in white light. So here I was on a Sunday morning on 24th of September 2011 with friends in visiting an amateur solar physicist who had built his own telescope above his house, and we didn't expect it. So we are in the rising phase of solar activity. In 2009, 2010, we are at a deep minimum in solar activity. Nothing is happening, and this is a morning where you look in the telescope, you see a nice sunspot in white light. And it starts to flare. This is like real. And you find out later that it's a big flare. It was an X flare. And this is when you apply a filter, an H-alpha filter. So after Carrington, the solar flares were observed with that kind of filter because it allows you to see smaller flares. So this event was quite large. We had so here we're looking at the photosphere, which is at about 6,000 Kelvin, about 7,000 degrees Celsius. When you go a little bit higher in the solar atmosphere, the temperature will decrease a little bit in the chromosphere at 3,000 Kelvin, and then it will increase very, very fast. And so in this image, we are already at 10 million Kelvin. Can you imagine? So we went from 6,000 to 10 million. So we are in the corona. And so you could see earlier a movie of the flare. This is observed with a telescope called the Solar Dynamics Observatory AIA telescope. And so you can see this flaring in, this is in a very hot bandpass of the EUV. And then what we do as well, I mean, the way of categorizing these flares is to look at them. You're looking at full sun, full disk, and you look at the X-rays. So these are curves, time series of the X-ray flux, and this is how the flares are ordered. You have the A, B, C level, M level, and X level is the one, and is the one where we have reached here. So, solar flares are one aspect of space weather. The associated counterpart of the solar flare, often associated with solar flares, not always, are the coronal mass ejections. So the flares are the let's say, light emission associated with an eruption, and the coronal mass ejections are the body mass, are the what's coming out of the sun in a bulk way. So what we have here is an event in in 2003, I believe. Yeah. So it was also a very large X flare. Actually, so large it's called X 17.2 because it's above that level, the X level. So they didn't have a name. They don't have XX, or so you add a few digits there. If you saw the movies, I will try to play them again. So we first have a view of the flare on the solar disk, and then what we see here are two coronagraphs. They are occulting the solar disk. So here the solar disk is just behind this little round here, and then there is more occultation, and what you see is the start of the coronal mass ejection as it travels outward sideways, but actually because it comes towards you, it's called a halo CME. And very quickly, so you can see it's all over the occulting disk. That means it's a halo, it comes towards the Earth. And very quickly what you see is a lot of particles hitting the instruments, and it creates some kind of snow. So these are the solar energetic particles. And in that particular event, it was so energetic, it hit and damaged an instrument that was on the 2001 Mars Odyssey, the instrument MARI. And you can see that very quickly, the solar energetic particles followed the solar flares. And here you can see within 17 hours of the event, we had actually an event that was out of scale. So you can see that it was not even possible. We were not used to even record this kind of event. Now, I will think needs to be, no, it starts. So this is now a view looking at the limb. So it's been moved to the side. It's looking at a particular active region on the limb. And this is again the Solar Dynamics Observatory, AIA. It's been treated so that it enhances all these structures. And so what you see here is the eruption of this coronal mass ejection. And you can see the flow falling back. And you can see, you can start to see a lot of motion as well. This is a very high resolution. There are other instruments with even higher resolution. The nice thing about this one is that you see the full disk. It's so nice, but I need to move on. So what I want to tell you about, I think I want to collect a few things that I really like about my field, are the Kelvin-Helmholtz instability. So this is a phenomenon that you know very well because you can see it at the interface between the sea and the air, but also on the beach, but also at the interface between the clouds and the air. So you have this, if you look sometimes, you can see that in the sky. You also have it in the atmosphere of Jupiter. You have this huge vortex that maybe you have seen before. So it's well known in the atmosphere. What's less known is how it behaves in Maritas plasma. So here we're talking about the solar corona, where you have a lot of flow, and this instability is driven by flow shear when you have a difference in flow. You have also the magnetosphere. The magnetosphere is also there is an interface between the fast solar wind and the stagnant magnetospheric plasma where this thing happen. And the heliospheric boundary. So the first one, the magnetosphere solar wind interface, we'll call it the magnetopause. The heliosphere boundary, the interface between heliosphere and interplanetary space, is the heliopause. It's also subject to this instability. You find it in cometary tails, and you find it in astrophysical jets. So here is like a simulation. You have magnetic fields between the two regions. So you have two regions, two different densities, and we introduce a flow shear. You can't have transfer of plasma between these two regions because the magnetic field stops the plasma from going across. So what you have here, you start to develop the Kelvin-Helmholtz instability because of the flow shear. And where you had initially magnetic fields parallel, all of a sudden inside this vortex, the magnetic fields can become anti-parallel. So in a different orientation, where we know that this is a good time for magnetic reconnection to occur. And magnetic reconnection is basically going to be an opportunity for plasma to move from one region to the other. And that's why it's becoming very important for instance, for magnetospheric physics, where we have the entry of solar wind plasma inside our magnetosphere. So we want to understand it better because it can create mixing, and we talk about mixing in the boundary layer around these regions. And it also, these vortices can merge, they can decay, and they can create turbulence. And so there's plenty of interesting plasma physics occurring. When SDO was taking pictures the first time in 2010, as I told you, there was not much happening. So we were at the rising phase of solar activity. And this one we'll see. And then we had this event on the limb. A nice coronal mass ejection, so it's been rotated. But because SDO was a very high cadence for the first time, looking at very high cadence, and also in that particular bandpass, which is very hot plasma, we were able to see the development of these Kelvin-Helmholtz waves at the flank of the CME. So you can see these ripples. It was so fast, so what you needed to do, you needed to take a snapshot, and every 12 seconds you had a picture, and you could see the ripples, and follow the ripples, and find that they would have, so this is a distance time plot, they would have a speed of about 400 kilometers per second, half of the speed of the initial coronal mass ejection. So the main speed here is about 800. So, and this is a typical result expected from linear theory. The phase speed of the Kelvin-Helmholtz waves should be about half of the driving flow speed. But what's also very interesting about this is that it introduces some drag on one flank of the CME. Right, so you can't see it on the other side. It's occurring on that side, on the northern side, which means that this side is slower than this lower side, which means that the lower side will travel faster. And eventually, we think that this could lead to some deflection in the trajectory of the CME. Now, understanding the trajectory of the CME is very important for understanding space weather, for understanding where the CME is going to hit the Earth. So understanding the properties of the Kelvin-Helmholtz instability is become relevant. How much time do I have? I don't know, when did I start? So here is the logarithmic scale of our position in the solar system. So we have the Sun and the interstellar medium, and they compete for control of the interplanetary medium. So this is our interplanetary medium, a logarithmic scale from the Sun to the Earth, 1 astronomical unit, then from the Sun to 10 astronomical units around Saturn, and then from 10 to 100, at 100, this is where, oh good, okay, so this is where you have the heliopause. This is the end of our heliosphere, but this is not the end of our solar system. So the difference between the heliosphere is what is controlled by the solar wind coming from the Sun. The solar system is what is controlled by the gravity coming from the Sun. And why the heliosphere is important is it's our first line of defense against against cosmic rays. And so you can see here the fraction of cosmic rays that are reaching our heliosphere has decreased by about 25% once we are in interplanetary space. And again, the magnetized plasma cannot mix. The boundary between solar wind plasma and interstellar plasma is known as the heliopause, as I've said before. I think what's nice about all the missions is that there has been some bold missions before. You may have heard about Voyager that crossed the heliopause, but we also have had a Ulysses that went above the Sun and that measured in situ the solar wind. And thanks to Ulysses, we know that there are two forms of solar wind: a fast solar wind at about 800 kilometers per second, and a slow solar wind of about 400 kilometers per second. And you can see that the fast solar wind is located at the poles above open regions. So this is the place that we call coronal holes, and this is where the flows can escape more easily than in the closed regions where the solar wind flows much slowly. So sometimes the coronal holes will drift towards the equator, and we can have some recurrent geometric storms because of that. So the recurrent because the Sun rotates with 27-day period. Another mission is that was launched in 2006. That is really a very important step in our field, is stereo. So stereo didn't have very fancy, very high resolution imagers. They had two things. They had imagers looking at the Sun, and they had in situ instruments measuring solar wind, etc. But what they had is that they were looking at the Sun away from the Sun-Earth line. So the first thing they did was, you had one called her head that went this way, and then the one called behind the other. And they went in quadrature in February 2011. That means for the first time we had a 360-degree view of the Sun. We could see everything on the Sun at once. And then they continued their route, and they crossed in 2015. This is when we started to lose stereo B, unfortunately, but stereo B is drifting, and there's still hope that we can maybe get contact with stereo B again. And so we still have stereo A and returning data. So we are looking at the Sun we've been looking at the sun in 3D for about 9 years, basically. And so in the first years, what you had is the two views, and the idea was to do a stereoscopic reconstruction. And in particular, this is very important to know the trajectory of a coronal mass ejection. Another nice movie that comes from Stereo is this one, Stereo A, was looking at the comet Encke, and this was the first images looking at the collision of the coronal mass ejection against a comet. And it caused a detachment of the plasma tail. So what we have next is a little simulation of that story, where you have comet Encke in the Parker spiral of the solar magnetic field, and the CME detaching its tail. Future missions, we have two very interesting future missions. One is launching this year, 2018, and it's Parker Solar Probe. And the other one is Solar Orbiter. Parker Solar Probe is a NASA mission, and Solar Orbiter is the ESA mission, European. Initially, we wanted them to go together. So basically, the idea is to go over the pole and very close to the sun. So as I said, I mentioned Ulysses went over the pole, but it was only with in situ measurements. So with Solar Orbiter and Solar Probe Plus, or it used to be called Solar Probe, now it's called Parker Solar Probe, we're going to be able to really get closer and see these regions that are difficult to observe on the pole. So about a third of an astronomical unit for Solar Orbiter, 60 solar radii, and about 9, even closer for Parker Solar Probe, 9 solar radii. 2018, that's this year, and Solar Orbiter 2020. So again, the Americans will be there first, but we can do some really nice research. Since I teach here, I just wanted to give you a taste of what can be done. So we have, of course, typical third year and fourth year undergraduate projects. There is a summer school. There are summer schools in many different places where you can go in your third to fourth year and even after. But we also have summer schools before you start a PhD. And we do a PhD. So it's all to do with space weather or the key regions of the Sun-Earth system. And we had a huge international astronomical union conference last July. We have the Met-Office that has been given space weather as a national risk since 2013 or 14, I believe. So we have good interactions with them. And we have the Norman Lockyer Observatory in Sidmouth that have their own little space weather monitoring. And I just want to mention, to conclude, that I have also a new module that you can take if you are in physics. It's an elective module that you can take, or if you are in mathematics. And before I finish, I have a little experiment that I wanted to share with you. So this is this is something, I don't think we're going to see much of it, but this one you can see from far. This is basically to show you how the Earth is going to react to interaction with a coronal mass ejection. So we have here a dipole, and it shows south-north. The south goes up And what we have then is a dipole field that is created. So if you do vector calculus, you can see this nice vector field. So what we have is the orientation of the magnetic field lines around the dipole. So what I'm going to do is I'm going to take one of those. That was here, this one. And I'm going to say this is going to be our Earth. So this is our Earth. Maybe it's a little bit too much. Okay, like this is our Earth. And I have another magnet, which is going to be our CME. No. So I have the blue. So if we have a northward, so the magnetic field here is northward. This is our northward magnetic field of the Earth. If we have a northward solar wind, we call it the northward magnetic field, IMF, interplanetary magnetic field. If we have a northward solar wind, so the blue align like this. Oops. Well, this is pushing, but nothing happens. Now I turn the orientation. This is now going to be anti-parallel. So we are having an opening. All of a sudden, you can see the needles here that represent the magnetic field. They want to push the other way around. So this is what happens with magnetic reconnection in a toy fashion. And I will stop here and take any questions you may have. Thank you.